Hi all, I am Professor Ravi Kumar, Assistant Professor, School of Mechanical Engineering, Shastra University. I welcome you all to the next lecture where I will introduce you about the isentropic flow, and we will also go through the isentropic relations, right, that will be used. So isentropic relations will give the relationship between the pressure, temperature, volume, right, either pressure ratio with temperature ratio or temperature ratio with volume ratio, or density ratio with pressure ratio. So let we are going to see what are those. So what is basically the isentropic flow? It is a flow which is reversible, adiabatic, and when a flow will become reversible, that is only possible if flow is happening very slowly. That we used to say, if flow processes are happening at very slow rate, so that each and every state passed through that flow will be an equilibrium state. Or if any change is happening in that flow, the change will be happening very infinitesimally slowly. if if such kind of process is happening, we'll say that process as quasi-static process. Now if there is no heat involved either to the flow or out of the flow, then it will be adiabatic phenomena. So a reversible adiabatic flow is known as isentropic flow. Why this name is coming isentropic flow? That knowledge you will get from the engineering thermodynamics. So isentropic flow is the flow along which there is no net change in entropy of the system. So entropy will remain constant while there is a flow from one point to the another point, and such kind of flow is known as isentropic flow. So, as a generic definition of isentropic flow, one can define in such a way: a flow which is reversible, adiabatic in nature is known as isentropic flow, right? Or you can say the flow in which entropy does not change, right, from one point to the another point. So these are the some of the characteristics of isentropic flow. So if I say isentropic flow, that will be termed as first characteristic is it is reversible, second is adiabatic, all right, adiabatic, right. Third, you can say entropy is constant along the flow, so entropy is not going to change. You can add two more things, right? There is no change in kinetic energy, there is no change in potential energy as well along the flow, and such kind of flow is known as isentropic flow. Usually an isentropic flow will be governed by equation that usually we say is given by P specific volume to the power gamma is equal to constant. So this is my equation number one. So any flow which is satisfying this equation, P to the power gamma is equal to constant, is known as isentropic flow. Even though for adiabatic flow also we use the same sort of relationship, but adiabatic flow will not be a reversible flow, flow, right? In which even though heat transfer may not involve, but we cannot reverse the direction of the flow. That means when we are defining a reversible process is a process which can change its direction without making any change to the rest of the universe. That means if it has started with 20 kilojoule of energy from one point and reached to the second point where its energy is only 10 kilojoule, now if I change the direction, right, to the reverse direction, again it will regain the 20 kilojoule without any loss of its energy, and such kind of process is known as isentropic process, right, isentropic process. So this is given by this equation. So from this equation, basically between any 2 points you can write in this way: P1 specific volume to the power gamma, the specific heat ratio, is equal to P2 specific volume to the power gamma. Easily you can write. Alright, so between 2 points I am writing. So if I take the ratio of pressures from here, P2 divided by P1, that will be given as specific volume 1 divided by specific volume 2 to the power gamma. This is my equation number 2. So I got this equation. So when we are analyzing any process, I usually we consider the perfect gas, right? Perfect gas or flow or ideal flow. And for ideal flow, basically the equation of our perfect gas we use to write in this way. For a perfect gas or ideal gas, usually we say PV to the PV is equal to RT. This is my second basically second equation which is in this way. I will say third equation in this series. So this can be written as a perfect gas. This is the ideal gas equation of state PV is equal to RT. So now I'm going to write the third relationship. Here I got relationship between pressure ratio and specific volume ratio. Now I am going to relate with some other ratio, specific volume with some temperature. I will try to do something, some arrangement. So I will play with this equation number 1. So how will I do that? So constant, this can be written as C. So from here I can say P is equal to C into V to the power minus gamma. If I take this divided by V to the power gamma, and V to the power gamma will become minus gamma. This is equation. Now what I will do basically, I will multiply here by V and I will multiply here also by V. So there is simple modification, even though this will cancel out the same equation which is written here. So this equation now is termed as PV is equal to C into V to the power minus gamma plus 1. Can I write like this? Or I can say 1 minus gamma. Yes or no? So minus gamma plus 1 can be written. What does this PV mean? So I can use this basically. Look at this term. So from equation number 3. So I will take the PV value from equation number 3 and substitute here. Right here. So this is becoming now R into T. I can write. So this I got from here. This PV value from equation number 3 I am writing here. So now I can make the necessary correction from here. So I will take this T this side. So I can write T into V to the power 1 minus gamma is equal to R divided by C. And for any gas, characteristic gas constant also will be the same. And this is the constant. So constant by constant is another constant, right? So I can say this is constant basically. This is constant. So between any 2 points, again I can write one more equation, right? This equation can further be written in between 2 points in this way: T1 into specific volume 1 minus gamma is equal to T2 specific volume 2 minus gamma, right? Yes or no? I can write it this way. So from this further I can get one more relationship, right? So what is that relationship? So if I extend this, I can get T2 divided by T1 is equal to, I am getting like this. So V1 by V2 to the power 1 minus gamma. Yes or no? Yes or no? Am I right? So yeah, it is going in this way. No, we had made a mistake here. Yeah, what is basically mistake we have made here, right? It is 1 minus gamma here. So if I take this term this side and I will write C by R, so I will make the correction here. Sorry guys. So this is now 1 minus gamma, this become gamma minus 1, and this term will be C by R basically. So C by R. So this complete term got changed, minus gamma minus 1, and here again gamma minus 1. So this is very simple. What exactly I did, this term is C into B to the power 1 minus gamma, right? Specific volume 1 minus gamma, and I switched to the value of T. So what I did basically, I had taken this V this side. So if I divide this V here, if I take up, this gamma will become now positive and 1 will become negative. That's why gamma minus 1. So here it is becoming now gamma minus 1. This is my equation number 4. Right, so I got these two equations basically. I got a pressure ratio here in terms of specific volume, and I got temperature ratio in terms of specific volume. So now I can use these two equations to write third relationship, right, between temperature and pressure. So how will I do that? So I will substitute the value of V1 by V2 from equation number 4, right? From equation number 4, I substitute the value of V1 by V2 where in equation number 2. So if I do so, I can write in this way P2 by P1 is equal to, in place of B1 by V2, I will write this term, that is T2 by T1 to the power, basically this will be 1 upon gamma minus 1 and whole power, already gamma is there, so this will become T2 divided by T1 to the power gamma upon gamma minus 1. This is my equation number 5th. So I got these some relations, right? I got one relation is this with the specific volume. I got second relation of T2 by T1 in terms of specific volume, and third relation I got here P2 by P1 in terms of T2 by T1, right? One relation. So now I will relate with density also, because that is also very important relation. So I am erasing here. So I will erase here. We know that specific volume is inversely proportional to the density, right? The mass density is usually written in this way. So wherever specific volume is there, that can be written 1 by rho, right? So I can write T2 by T1, right, again from equation number 4. I can write T2 by T1 is equal to rho 2 by rho 1 to the power gamma minus 1. This is the one relation which I got. Yes or no? So T2 by T1 is equal to rho 2 by rho 2 power gamma minus 1. This is another relationship. This is of 5th. I can say this is 6th. Right? Now I know all the relationship between temperature ratio, pressure ratio, temperature ratio, specific volume, and temperature ratio with density as well. Let's go for now the stagnation and static properties relationship. So stopping here. Now go for the next things. So the same relation I will be using there. So note down these all things, right? Let's go for stagnation properties. So stagnation point first need to be defined. What is stagnation point? A stagnation point is a point in a flow which will we obtain if a flow brought to rest isentropically in a reversible adiabatic zero work output device. Condition is reversible adiabatic zero work output device. So if all of a sudden you are bringing a fluid which is moving to rest, right, without doing any work on it or without getting any work out of it, and a steady condition, a steady adiabatic zero work output device, such a point is known as stagnation point, or it is a point in the flow where velocity all of a sudden comes to zero, is known as stagnation point. So velocity all of a sudden comes to zero, that means all of the kinetic energy is getting converted into the pressure energy. So that means pressure energy will be more. So whatever energy we are getting there, either enthalpy, let's suppose enthalpy, the whole of the kinetic energy got converted into enthalpy. So enthalpy will be a maximum. So at that point, whatever properties we are getting, so those all properties will be known as stagnation properties. So the stagnation condition basically used to be considered as a reference in a compressible flow basically. So whenever we are dealing with the compressible flow, we need to take a reference as a stagnation point. So all the properties as stagnation points are stagnation properties, and all the properties, right, denoted by suffix 0, right, it will be designated by 0. So if I want to write pressure at a stagnation point, that will be P naught, temperature at this point will be T naught. If I write enthalpy at this point, that will be H naught. Similarly, rho naught, etc. can be written. Speed of sound can also be written as A naught. So property denoted by 0 suffix will be stagnation property. So let's start our derivation part of it, how to relate with the Mach number, because these stagnation condition will be existing only for compressible flow, and when we are dealing with the compressible flow gas dynamics, we have to relate all the properties with the Mach number. So let's consider the energy equation, right? So I am drawing here enthalpy versus entropy, right? So I cannot go in that much depth because it's the part of Engineering thermodynamics, already you would be knowing that you are going to study this thing in your basic fundamental engineering thermodynamics. So enthalpy and entropy, I am drawing one curve. So what is total enthalpy? As I said, when flow is moving like this, all of a sudden it comes to rest. So the point where it is coming to rest will have maximum possible enthalpy. You cannot cross that. That will be constant. So I can draw a line here, that will be representing simply the H naught or enthalpy at a stagnation point. So there is another initial enthalpy, right, which has been provided to the flow, so that the flow has started from some point. Let's suppose I say that enthalpy as H, right. From there flow is basically traveling, right. And how actually flow will happen? In order to have a motion, we should have a pressure difference, right. So at two different locations I will have a pressure difference, and between that flow is moving. So between that flow is moving, so let's suppose one pressure is going like this is one pressure line, this is second pressure line, this is static pressure basically, and this is stagnation pressure because it is at a stagnation point. And these all two lines are constant pressure lines, right. This static pressure constant pressure line, this stagnation pressure constant line. In between that, right, whatever this enthalpy difference is there, that is nothing but why this I am getting H naught, whole of the kinetic energy is getting converted into the what, enthalpy rise or pressure rise, right, at that point. So kinetic energy is half c square, right, basically. So c is the velocity of the flow, right, c is the velocity of the flow, so half c square. So I can write the equation here, H naught is the total enthalpy is equal to H at this point plus c square by 2. C is the local velocity of the flow, right. This is my equation number 1. And for perfect gas, basically for perfect gas, enthalpy is a function of temperature alone, right. Enthalpy is a function of temperature alone. And also we know that enthalpy is nothing but Cp times of T, right. H is equal to specific heat at constant pressure into T. This is called enthalpy. So if I substitute these values here, I can write this as H naught minus H is equal to C square by 2. Yes or no? So I can write this further as Cp T naught minus T in absolute temperature is equal to C square by 2. So that can further be written as T naught minus T is equal to C square by 2 times of Cp. Right? I can write in this way. Again, if I divide both sides with the static pressure, static temperature T, if I divide that, the same equation I can write in this way: T naught by T minus 1 is equal to C square divided by 2 times of Cpt. Yes. So now from here I can write further simplification: T naught by T is equal to 1 plus this one is going this side, C square divided by 2 times of Cpt. Yes, no? This is my equation number 2. So I stop here. Now I have to do some more modifications to it. So in order to relate this temperature ratio in terms of Mach number, how to do so? So I will be starting here. Basically, specific heat at constant pressure is nothing but gamma times of R divided by gamma minus 1. This is one of the empirical relation that you will study. Like Cp is this, and Cv specific heat at constant volume will be R upon gamma minus 1. Alright. So I will be using this here, right? Gamma R upon gamma minus 1. Now question will arise how actually this thing is coming. This is basically is very simple. You would have studied this Cp minus Cv is equal to R. This you might have studied somewhere, right? Yes or no? Yes. So on a specific heat ratio, right? Gamma is nothing but Cp by Cv. This is not a specific heat ratio. So what you need to do here, if you divide this complete equation by Cp, right, if you want to relation of Cv, or if you want only Cv, divide this complete equation by Cv. So if I divide this complete equation by Cv and here Cv, right, so So you can get here Cp by Cv minus 1 is equal to R by Cv, and the Cp by Cv is what? Gamma, which is given here, right? Cp by Cv is gamma. So this will become gamma minus 1 is equal to R by Cv. So Cv is equal to R upon gamma minus 1. This is very, in a very simple realistic way you can get Cp value. The moment you know the Cp value, you can substitute here to get the Cp, right? So this initial value, initial equation was Cp minus Cv is equal to R. This was the initial equation, and you divided by Cv and you substitute this value, you got this. Now you substitute this value here in Cv, R upon gamma minus 1, right? You do that, right? You can do that. You substitute this value here. So if you substitute that value here, you can get Cp as well. So Cp and the Cv is R upon gamma minus 1 is equal to R. Take this side. So Cp will become R plus R upon gamma minus 1. So gamma minus 1 is LCM. If you take, and R is common, so gamma minus 1 plus 1 into R, so plus 1, this cancel out. So this become gamma R upon gamma minus 1, this is Cp. So you got these both relations, right? Cp and Cv. So directly you will be using here. So Cp you can substitute here, right? So this you can note it down. So I am substituting here. So T naught by T is equal to 1 plus C square by 2, and Cp is gamma R, right? So gamma R I have taken, and T I will multiply, and bracket gamma minus 1 is coming up, right? Divided by 1. Something gamma R, gamma minus 1. So this what I am doing basically, 1 plus gamma minus 1 divided by 2 I have taken, gamma minus 1 divided by T into C square upon gamma RT. And what is this basically? Gamma RT, I somewhere mentioned a local speed of sound, right? So local speed of sound is given by under root gamma RT. So this is nothing but local speed sound whole square. So this can be written as 1 plus gamma minus by 2 C divided by A whole square. And Mach number is nothing but local speed of flow divided by speed of sound, right? So Mach number is nothing but C divided by A. This already you know. So you substitute here. You can write direct relation T naught by T is equal to 1 plus gamma minus 1 by 2 m square. So this is my first equation in terms of Mach number, stagnation temperature, static temperature with Mach number. Alright. So now you look at if you use now isentropic relation, right? So use the relationship of pressure with temperature. So as you know, P naught by P is equal to T naught by T to the power gamma upon gamma minus 1, that is nothing but 1 plus gamma minus by 2 m square whole to the power gamma upon gamma minus 1. Similarly, you can write for density. Density naught by density is equal to T naught by T to the power 1 upon gamma minus 1. So this can be written as 1 plus gamma minus 1 by 2 m square to the power 1 upon gamma minus 1. So you got three relationships, right, to get pressure, temperature and density at a stagnation point, and these all rho, P and T are the static properties. So this is a ratio of stagnation to static properties with Mach number you can get. Now the question arises, how basically in airspeed indicator problems you were writing 1 by 5, and for air you know gamma is equal to 1.4 is a fixed value. So we substitute here 1.4 1.4 minus 1, that will be 0.4 divided by 2, right? This will become 0.2, and 0.2 is nothing but 1 divided by 5, can be written as 0.2. So here 1 divided by 5 I can write. Similarly here gamma upon gamma minus 1 is 1.4 divided by 0.4, right? So this become how much? Basically this become 14 by 4 or 7 by 2. So 7 by 2. So this bracket term you can write directly for air. Basically this is for air. I can write T naught by T is equal to 1 plus 1 by 5 m square. Very simple relationship. I can relate So similarly, this can be written. So P naught by P is equal to 1 plus 1 by 5 m square to the power, this term is I have written 7 by 2. 7 by 2. Very simple way I can relate. So in this way, you can derive expression for the stagnation property with the static property in isentropic flow with Mach number, right? Very simple. Sometimes, yeah, they used to ask determine the critical properties. So that also I will give you here itself. By that I will conclude this lecture. So critical properties. So in the flow, the flow will become critical only when my Mach number is reaching the sonic speed, or I can say when Mach number is becoming is equal to 1, when Mach number is equal to 1, right? My flow properties will become critical properties, right? So if we consider flow through a nozzle, right? So conversion diversion nozzle, right? This kind of shape nozzle, right? If your flow is taking place, right? So a point will reach when Mach number is equal to 1, my flow will get choked. That means the condition at which I will get maximum possible mass flow rate. Beyond that, there is no increase in mass flow rate, and such condition is known as choking condition or critical flow condition. So critical flow condition will occur when Mach number reaches 1. So in nozzle, always keep in mind at the throat portion, this is basically throat area. In throat section only you will get m is equal to 1. So the moment your m is equal to 1, your flow will be choked, and you can say it is a maximum possible mass flow rate which is possible in this nozzle, and flow properties will become the critical properties. So all critical property will be designated by a suffix star. So whatever property you are writing, P star, T star, rho star, these are all critical properties. So this condition will happen only when your Mach number is equal to 1. So if you substitute that value in Mach is equal to 1 in this equation, right? If you look at this equation, alright, so I will be using this same equation from here. So if Mach is equal to 1, my static temperature will become critical temperature, but stagnation property will remain the same because those are the initial condition in the flow. So I can write this equation here in this way. So I can say T naught by T star is equal to m is equal to 1. So I can say 1 plus gamma minus 1 by 2. Take 2 as LCM. If you took the 2 as LCM, I can write gamma plus 1 by 2. Right or not? So I can say T star by T naught is nothing but 2 times divided by gamma plus 1. This is one relation which you got. Right? Similarly, you can say P star by P naught is equal to 2 upon gamma plus 1 to the power, this is gamma plus 1 to the power gamma upon gamma minus 1, and rho star by rho naught is nothing but 2 upon gamma plus 1 to the power 1 upon gamma minus 1. So these are the relationship for critical properties with the stagnation properties. Keep in mind the Mach number is equal to 1, my properties will be critical properties, and critical properties are designated with the star, and stagnation properties are designated with naught. So don't get confused, and when we are dealing with the speed indicator problems, I used the naught for sea level condition as well. Or sometime if you are getting confused, right, you can write for sea level properties as P sea level, right, rho sea level, like that. These symbols can also be used, right? Don't get confused. But stagnation properties always be designated as naught. So P naught, T naught, rho naught, these are all stagnation properties, and the star, P star, T star, and rho star, these are the critical properties, right? Whether this is clear to you? So conclusory statement for today, I have given you an idea about isentropic flow, what is isentropic flow, and we have seen the isentropic relationship between the pressure, temperature, density. We have also covered a derivation of the stagnation and static properties with the Mach number, which is very essential for compressible flow. So whenever we're dealing with the compressibility fact or compressible flow, you have to relate the stagnation property with the static property with Mach number. Because in compressible flow domain only Mach number is the first primary criteria that need to be known, and based on Mach number you will decide whether we are in compressible medium or we are in incompressible medium. right? I said there are some threshold value, point less than 0.3 Mach number can be treated as incompressible. Going beyond 0.435, then everything is compressible, and you need to consider compressibility into your mind when you are making any performance calculation. So the this relation also got derived today, and we have seen even critical flow properties. This will happen only when Mach number reaches 1 at any point in the flow domain. At that point, it is the maximum possible mass flow rate which will be obtained from that duct, right? It's either constant area duct or conversion nozzle, right? You will get Mach is equal to 1 condition, there only you will get the critical properties, or you can say that is the maximum possible mass flow rate. Beyond that, you cannot increase. So at Mach number 1, whatever properties you are getting, those are all critical properties, and all critical properties are designated with the star value and star. So we have derived the relationship for stagnation with the critical, right, in terms of gamma. So this is also fixed value, as you know, for gamma value is fixed for different gases. Is air, gamma is equal to 1.4. If you substitute some value, you will get some value out of this, right? T star by T naught some constant value, P star by P naught some constant value. So you can easily find out the critical properties, or sometimes some multiple point of stagnation property, 0.3 or sometimes 0.588, those kind of values you will be getting. So we have covered today stagnation relationship, isentropic relationship, and these are also isentropic flow. Basically is applicable only for isentropic flow. When compressible flow domain also, you need to assume isentropic flow condition, and you have to analyze the problem. So with this, I am stopping the today's lecture. So if you are still having some doubt, you feel free to ask in the comment section. I would be happy to solve all your queries. So thank you very much for listening and giving this much patience, right? Please like my video and subscribe my channel. You can share this with your friends, guys, who are needing to understand the concept of isentropic flow. Thank you very much, and have a nice day. Good day.